Alright, here we go. We are live, I think. Hopefully. Yes, we're live, and YouTube says we're in excellent condition, so that is fantastic. My name's Tom. I talk about code. Today we're going to be learning Rust. I've been writing a little bit of Rust, but I'm not very confident with my Rust yet, so we're going to be diving into the wonderful world of Rust. My microphone alignment looks pretty good. This should be okay. I still have my janky pop filter that is an embroidery hoop and a crappy bit of wire. It still jiggles around while I talk. That's fine. But yeah, we're going to be writing Rust. We're going to be building a simple virtual machine, a little 16-bit virtual computer that's going to be able to do all kinds of fun calculations. We're going to do fun stuff with it. But first off, we need to kind of set up a Rust project. We need to learn how Rust works. What are lifetimes? Okay, but first, the most important thing, I just need to dump a link in my Discord server, which you should think about joining if you like hanging out and talking to cool people about cool code. So we're gonna just quickly say announcements. Live. Awesome. Hope everyone's doing well. Oop. Perfect. Okay, so let's write some Rust. Let's dive in. This is an empty folder. So the first thing we're going to do is a cargo init, and this isn't what I want. Straight off the bat, we're hitting something I don't want. So this is a binary application. If we look at cargo toml, if we look at the source file, we just kind of have a main. We don't want a main, we want a lib.rs. We want to have our project set up as a library because we're going to have a core part of this project that's going to be shared between a couple of binaries. So let's delete everything in here. And let's see how to actually use cargo init. There is a lib option. So let's do this. I don't think there's too much crazy stuff we need to think about here. Wow, it supports fossil. That's really cool. Okay. Cargo init lib. Perfect. Now, instead of a main.rs, we have a lib.rs. Our project is set up to not build a binary. So if we cargo build, great. If we cargo run, nothing happens. There's no binary that can be run. So, cool. Let's get rid of all this. We don't need any of this. What happens if we cargo build now? Excellent. It builds nothing. There's no code to run. So we've got a project. We've got a thing set up. And this is good. And this is good. The first thing we want to do is to start to start to make a couple of definitions. So let's go into our source and let's make the shell of what a virtual machine will be. Okay, it's going to have a struct. We're going to call it machine. And what does our virtual machine need to have? Well, it's going to simulate a computer. We're going to need a couple of registers. And this is going to be an array of 16-bit unsigned integers. We're going to have a couple. Let's say 7. This is what I was kind of playing around with at home. It's going to be a 16-bit virtual machine, so our registers are going to be 16 bits wide. We need to have some memory. Okay, this is going to also be actually no, this is going to be unsigned 8-bit integers, and let's say we're going to have like 5,000 for now, but that's a bit of a funny number. We need a better memory interface soon. And is that it? Is that all we need? We're going to have things like a program counter, we're going to have a stack pointer, but these are all going to live in registers. There are going to be implications to this, but this should be fine for now. So what are our registers? Well, if you're working in a language like Python, you might make a const called reg a. You might make a whole bunch of constants for different registers, but because this is Rust, we're going to use an enum, which again has implications. You may be able to argue that constants, have less overhead, I guess. I think Rust enums do actually come with a little bit of overhead, maybe not when you define them like this, but we're going to have registers A, B, C. We're going to have a stack pointer, we're going to have a program counter, we're going to have a base pointer, and we're going to have some flags that can do different things. And let's also have a register called M. How many is this? 1, 2, 3, 4, 5, 6, 7. This is 8. This is too many. We need 8 here. If you've built virtual machines before, you might recognize what some of these will be for, but we'll talk about them as we get to them. These are all basically just magic names. You could define these as just general purpose things, but we want to give them special names because they will have special meanings to the actual inner operation of the machine. Excellent. Okay, so what does a machine do? We're going to have a function new, which is just going to create a new machine. Perfect. Self. We're going to have, it's just going to be initialized to 0. Our registers, everything's just going to be 0. Our memory is also going to be 0. It's going to be 5,000 of them. Now, you're going to notice a problem right off the bat, which is that we have to repeat these numbers. We'll see. We'll see where we get to with this. I actually don't know precisely what's necessary here. We can play with the syntax. And then the other thing the machine needs to do is to like run a program, right? What does that even mean? Well, a program is just a bunch of stuff in memory. It's gonna let's start to hack this out in code. That's even better. Let's say step. And this is gonna return probably some kind of result. Let's maybe... I like to just hack out my results. Actually, maybe it's... I like to hack it out just with, like, inline static strings. That's okay. That's okay. And if you're watching this and thinking, wow, this guy knows a little bit about Rust, this is like the part of Rust that is like other programming languages, right? This is the part of Rust that's a bit familiar. So, you know, there's nothing too crazy going on here. There's nothing too crazy. When our virtual machine runs, right, we're going to run a program. Our virtual machine binary is going to call step on our virtual machine. We're going to step, we're going to step, we're going to step, we're going to step until our program is done, and then we're going to have some kind of outcome. And again, outcome, input and output, these are all things that are very complicated, and there's going to be a lot of things to consider. But for now, when we step, we're going to we're going to need a few things. So first off, we need to actually take a reference to ourselves. When you define a method or like a function that operates, you know, on a struct in Rust, I guess, I don't know if Rust calls them methods. They're kind of what you would think of as methods in a language like C++. You can do this in a few ways, right? You can say, well, we take and like kind of consume ourselves, we borrow ourselves. We actually want to say we mutate ourselves as kind of like or we mutate a reference to ourselves. It's kind of like taking a pointer, but taking a pointer that we are allowed to change. So let's just like, let's define things in variable names because that's going to be clearer. Registers. Now, this isn't going to work. We can't reference a slice, an array with an enum. This will just blow up in our face, but we'll get back to that. We have program counter, then we're going to have to say self. Okay, so we're going to run into another thing right off the bat, which is that our memory is a slice of unsigned 8-bit integers, and we want to read a 16-bit instruction from it. Because this is a 16-bit computer, we're going to make our instructions 16 bits long, but we don't want our memory to have to be, you know, like if we make this 16, then it kind of raises questions about how we would store individual bytes. So we'll make this 8. We'll make this unsigned 8-bit integers. That's kind of a very pure way to think about this, okay? So actually what this is starting to lean towards for me is that we don't just want a dumb array, we want some kind of interface. And you know, if you reach for the word interface, again, if you're coming from Java, you're kind of reaching into Rust traits, which are different but serve the same purpose. So let's say we have let's call it addressable. I think that's the right number of D's and S's. But I always love spell checkers in chat or in comments if I've spelled things incorrectly. we're going to have a couple of functions. So if something's addressable, right, we can read from it, which means that we take an address, which is a, well, 16-bit, because this is a 16-bit computer, let's say a 16-bit address, and we get an 8-bit number back. And we can also write, which, which means we take an address and a value, and we try to write it to that address, and we get nothing in return, right? And I think we need to end these with a semicolon. We'll find out when we try and compile it. Let's see. So read and write. Except this doesn't quite fully satisfy me, because what if we're trying to read and write out of bounds? So let's maybe make this an option. And let's say when we write, we give back a bool rather than an option or something. There's nothing we're actually handing back, so let's keep it simpler. Okay, but this is just for 8-bit reads and writes, right? So then do we need read to which option U16, and similarly, let's say write to which, again, kind of does the same thing, right? Rust lets us do something really cool here, though, because while it may be nice to specialize these, we can actually provide a default implementation that just relies on having read and write defined, right? So what this means is that if something is addressable, you can define read, you can define write, and then you get these bigger reads and writes just for free. And we could even do other things, like say maybe have a copy function where I'll do this in memcopy order if I can remember memcopy order. From to n, right? Where, we read and write, and we can provide an implementation of this just based on read and write, where we copy a block of memory from one location to another. So let's do some janky default implementations here. Would a result type, sorry, I've got a comment in chat from Myopic Squirrel. Would a result type with an empty OK variant not be preferable for the bounds error for write? Potentially, right? In this case, it either succeeds or it doesn't. I don't know if the overhead of a full result is worth it. It definitely encodes the intention more, but I don't know what the actual thing would be here, right? Like, what information can we provide in the failure case of this result type? Unless, unless you mean, like, we could do that, right? Like, no information is encoded in a failure here. So I feel like this pretty much just reduces down to a bool. Does that make sense? It may be less idiomatic, and I might regret this and change it later, but I don't really see the value in a full result type because there's no information to actually encode in the error. I feel like that's one of the valuable things about a result type. Like, you actually, there's something in the error that you pass out. You encode more than just success or failure. A bool, in the case where it just succeeds or just fails and there's no extra information in either end of the type, I think that's okay. Things that consume addressables will definitely interpret this as, a false there as a result. Could there be multiple failure modes? Potentially. For now, the only failure mode would be address invalid. What invalid means might have more nuance, but for now I'm going to keep this as a bool, and as I said, possibly regret it later. But yeah, more failure modes does imply that a bool is inadequate here and a result type would be better, but until I know what those failure modes might be, and if they even really exist, I'm going to keep it as a bool. So read to. So instead of just reading one byte, we're going to read 2 bytes and mash them together. So we're going to say let's say if let sum x oh, hold on, I've also missed something very important here. I always forget this when I'm writing Rust. I always forget the self. No, Myopic Squirrel, thank you very much for asking. That made me think about a thing that I had not totally considered, and that is what I love when I am learning. So thank you very much. And how you going? Where are you from? I don't recognize the name necessarily. Have you hung out in my streams before? It's also been a little while since I've been streaming regularly. I've probably forgotten people. Cool. So we now can actually like reference ourselves in these methods. So if we're reading 2 bytes, what we really want to do is read a first byte from the address, and if that is something, then we want to say, I'm going to do this really jankily, aren't I? Also, this is the point where I decide if we're little endian or big endian. Yeah, x1 is so if we successfully read 2 sequential bytes, we're going to return so little endian. So the smaller address has the lower 8 bits of the final word. I'm going to be extremely liberal with my casting here as well, because I think I'm going to have to say cast both of these to U16s to combine them like this, and this has to be cast to a U16 before I left shift it, otherwise nothing's going to really work. My Epic Squirrel just stumbled on to my stream while debugging some Pio3 code. Procrastinating, UK based. Awesome. I'm never really sure what time I should be live streaming because I'm in such a different time zone to everyone else. Now this is kind of funny, right? Because I've got these nested if statements. I end up in this funny situation. So maybe I'm actually better with a return here. And then I say none. But then I need a semicolon. So this is a whole expression, and this whole expression evaluates to nothing. I don't know, this is just like a funny little nuance thing. Right is going to be similar if, well, we need to decompose the value into 2 bits first. So let's say let lower equal value, and oops. If you see me typing funny, it's because I'm using a very tiny keyboard and I don't program much for the last 2 months, so I've kind of forgotten how to use it. Oops. Value, and so we're just extracting the 2 bytes here from our 16-bit word. 8, sorry. And we're going to have to convert these to U8s at some point, but we're not going to do that yet. Cool. So, you know, we kind of extract the byte that's in the lower part, that's fine, and here we extract the byte that's in the upper part, mask it out, and then shift it right so that it has the correct value. If you get the shift, you get all kinds of kooky answers, but you will, when you write things like this for the first time, forget that shift, and then spend a long time pulling your hair out. You learn these things the hard way. Awesome. So, what I think we actually want to return here, we can do some funny logic short-circuiting, right? Because we can say self.write add a lower, and wait, which one is this? We want it to short circuit, so we want it to be an and self.write. So what we're saying here is, because these return bools, we can do this cool combination, right? If this is true, if this is false, then we won't even evaluate the second part of this. But if a right fails, there's something bigger going on here. So we don't need to really, we don't want this to go ahead if the first one fails, and logical short-circuiting means that won't happen, but it's also not super important. We can also do this copy for now, let's say for I in, can I do from to like that? I think that's Rust. We'll find out in a second. I'll try and build it and see what happens. I don't have any IDE hints, right? I'm kind of flying blind, and I love doing that, especially with languages I don't know, because it means I have to be very conscious of what I know and what I don't know. That's actually not what I want. Hold on. What am I saying? 0n. Let's actually think about what we're doing here, right? Self let let's just call it x self dot read from plus I, and then we'll say self write 2 plus I, and the value is just going to be x. If this fails, hold on, let's this returns an optional, so we need to do this nested thing, else false. And now we're getting into this kind of situation where, yeah, like maybe there are actually different failure modes. Maybe we care about which exact address generated this fault. So maybe we're already starting to regret this, but let's see where we go. Let's pull the thread a little bit more. If this fails, then we're going to return false. Cool. And let's see what happens if we cargo build this. And that works. And of course that works because cargo does not care that anything in this file exists, because in our lib.rs there's nothing. So let's say mod, I think we say mod VM, I think. Even better, let's say pubmod VM, because then things can actually use it. And now we're going to get errors. Yes, excellent, excellent. Okay, so straight off the bat, I forgot to do something, but let's jump into this thing I kind of called out. We can't do this. We can't index a slice. Oh, well, we can't index an array, sorry. This is actually just an array, not a slice, I think, because there's no like ampersand at the front. We can't index it. This needs to be a usize. So I think I should be able to say as usize. Also, we just kind of left this dangling. So memory dot read to PC, and we'll die if it's not the thing we want. And we'll just print this out because otherwise the compiler will complain. Cool. Okay. So we got rid of one thing. And then we need to say okay. That's the other important thing. Classic Rust compiler error where you try and return a thing as the last statement, but you put a semicolon in, and so nothing comes through. Excellent. Excellent. And I love the Rust compiler errors, right? Because no method named reto found on this thing, but it detects that there's a trait nearby that defines this. And so maybe we should implement it. That's a really cool, useful helper. Okay, so rather than having a dumb array, so now we're going to have, now this is going to be tricky, right? Because we can say impl addressable. You can't just say addressable, right? Let's follow this down. Let's see the errors that come up. Addressable, right? Trait objects must include the dyn keyword. So what happens if we put dyn here? What if we follow what the compiler says? The size for the value can't be known at compile time. Well, first off, I mean, you know, this doesn't work. So let's fill in the other gap here, which is that we need to actually make an addressable that we can put here, and we'll say like linear memory new. Cool. Because at some point we might have non-linear memory. We might define memory that has a gap in it or something. It's going to be hard to do too many meaningful things with a 16-bit address space. We might bump this up to 32-bit at some point in the future, but for now, it would be kind of funny to have a 16-bit machine that had 32-bit address space. I don't know. Let's start with this. This might be over-designed, is what I'm trying to say. Cool. So we're gonna have linear memory. It's gonna have. Let's call it bytes, and this is gonna be vec of u8s impl pub. So we're gonna have this should take a size as well, right? How many bytes do we, or how many bytes do we want in our linear memory? We're gonna return a new vector of size n that is 0 initialized. And now we want to implement addressable for linear memory. And all we need is read and write here. So let's just jump up and copy these function signatures. Okay, so if adder is less than hold on, this needs to be here. And then this is here. Cool. Okay, if the address is less than the size, then we return some value. Actually, hold on. Can't I just say self bytes get? Doesn't this already just return an option, maybe? We'll find out. We'll find out when I try and compile. The compiler will fix everything. And then if adder is less than self.size. So if the address is in bounds, then we're going to say self.bytes adder is value true. Cool. And because we've implemented these two things, we don't have to implement read2, we don't have to implement write2. We could, if we wanted to make, maybe a more efficient implementation or something, but we just don't need to. So now cargo build should have, okay. Let's do it here because we can scroll around more. Okay, so the first thing it's saying is that I have not bracketed correctly. I can never tell how grabby, what the priority of as casting is, but apparently this is not correct. It needs another layer of brackets. As casting in Rust, casting with the as keyword really does generate a lot of brackets. It's a little bit sad. Oh, oops. And of course, I forgot this needs to be a sum. Oops. Here we go. So and now we've got this problem as well, where we need to cast things as u8, as u8. Another case where we need to cast something from, oh no, hold on. This cast is dangerous. There's definitely something else I should be doing here. Because just casting a U size to a U16 is a little bit dangerous. There's an extra parentheses here, but that's weird because it just told me there weren't enough parentheses. I as U16. Okay. Wow. But this is good, right? I love how detailed these all are. Oh, copy, of course. If the copy gets all the way to the end, then it succeeded. And actually, we don't need the return there. We just bang true down. The last expression, that's what returns out. Slice indices are types of U size. adder. Okay. So this case, however, is a lot better. As use size. So this is kind of like, we want our API, we want our function signatures to represent the 16-bit nature of this machine, but Rust actually demands other things for very good reasons. Self bytes. I thought, this is funny. Okay, this is very funny actually, because it's trying to borrow. See, this is weird to me, right? Because I get why. I get why this happens, because if you have a more complicated type that you're getting, then yeah, you don't want to copy it everywhere. But in this case, I actually want to get, like, I want to take ownership. Well, I don't want to take ownership, but I just want a direct copy of this thing. I don't want to borrow it. I just want a copy of it. It's just a freaking byte. You know, it's wrapped up in an option, but it's just a byte. Just give me a byte. So I'm gonna see if I can do this with something else. So if adder less than self.size, some self bytes. Because I don't want to have to change this to this. That's silly to me, because this is just a byte. Okay, else none. What does this say? This freaking comparison again. As use size. I hope that these casts are compile time, not runtime. Oh, where did that come from? Okay, so there's like some syntax error here that probably came from my refactor here. Myopic Squirrel says, does using a vector rather than an array not mean that memory isn't going to be on the stack? Yes, that's true. I'm pretty sure that vectors don't go on the stack. But if I use an array, it can't be dynamically sized. The array has to have a fixed size. There must be a way to do that on the stack, but honestly, like, I'm just going to put it on the heap and it's okay. Maybe at some point, because of how I've written this, like, it would be very easy to change this type in the future. That'll just get absorbed, you know, in these two methods. Like, the default stuff, like having these two methods and then default implementations for everything else means that that's kind of easy to do. But yeah, vector for now. I don't know Rust, so I can't give a definitive answer. I'm pretty sure that means it goes on the heap. I'm pretty sure that, because if you have an array, for example, let's say I make this like, you know, this would need to have a fixed size, and maybe I could just make that 16, what is it, 16.6, whatever the maximum 16-bit number is, but I'm going to make it dynamic for now. But yeah, no, it's a good point. It's another good question, and it's one I wish I could answer better. Okay, there's a syntax error here. While parsing the struct, like, why does it, like, what's going on here? What's happening here? There's something very wrong. 56 option here. Something very, very wrong is happening here. It doesn't even know where it is. Like, it's trying to parse a struct. That doesn't sound right. Also, I appreciate the wording recovering Python dev from Myopic Squirrel. That's good. That's very good. Cool. Recovering Python dev. It is kind of bad, right? Python is just so, like, easy. So easy to just throw stuff together. You can really get into a lot of bad mindsets. And when I say bad, you know, sometimes just getting shit done is the right mindset, but not always. Sometimes you have to, like, write code with other people. Sometimes you have to share. Okay. Try naming a field sum. Oh, huh. Okay, if you're watching this, have a think about what this error means, right? Let's go back to it. Bracket is interpreted as the start of a generic argument for usize, not a comparison. It literally tells you exactly what's going on. It's trying to read this as if I'm saying this, right? Because usize is a type, and when you're parsing a type, brackets, angle braces mean something else. So what I need to do is wrap this in brackets. Again, so what happens is as has a higher priority, but usize kind of leaks out to the rest of the statement if it doesn't have a bracket. Now, here's a problem. Here's a good problem. Dynaddressable. So there's a bunch of stuff going on. There's a bunch of stuff. Let's also just do this. Let's say like 5 times 10. Say 5 kilobytes. Oh, let's say 8 kilobytes of memory. Oh no. I need to replug my keyboard, sorry. Frankel TY is not a kind of operator. What is not a kind of operator? Okay, so we have this problem, right? For one thing, so this all seems to come back to this problem where we don't have a size known at compile time. Frankly, he's pointing out the thing I said. Angle braces can mean different things. Well, it's really interesting that this is the generic syntax that we've settled on for so many years. But anyway, we have this problem. Because the size of this thing is not knowable, right? The thing that implements this trait, we don't know how big it is. So there's a couple of ways that we could fix this. I don't think this is one of them, but this is another lever I know I can pull. Infiltrate in function. Oh, okay, yeah. So, okay, that's not how you do things. So there is something we can do, right? And that is to make it a box. In other words, a thing that, like, be explicit that it lives on the heap. And this will let it work, right? Because we're basically saying, well, you don't need to know how big this thing is. You just reference a thing on the heap. Excellent. And that actually works. That worked. All we got there were warnings about things never being used, which is weird because we do actually use this enum, right? Like, excuse me? We definitely use this. Frankelty says, Rust tries to be easy version of C++, but it drives me nuts. I don't know what you mean by easy version of C++, because I definitely... Like, C++ is a hard language to write because it's so big, but Rust is definitely hard as well in its own way. Okay. Now, we can get rid of some of these warnings by making them pub. And we definitely want these things to be public. I also think we've got a lot of different concerns going on in this file right now. Look at that. Holy crap. Oh, of course it says register isn't used because the only use of register was in a function that isn't used. That's how smart the Rust compiler can be. Beautiful. Okay. So, let's just split these things out into some smaller files. Just for now. Just because it's gonna be easier. It's gonna be easier to think about where these things live. Addressable, cool. Excellent. And then we need to say use crate memory. Cool. We're going to grab those in. But then we're also, I think, going to have to go into our lib.rs and say pub mod. I think we're going to have to do this. And that builds. And when we try and run it, nothing happens because we don't have a binary target. So let's make a binary that is actually going to run our virtual machine. So if we go into our cargo.toml, we can define a binary target. And I did a little bit of research about this. And I'm going to sneakily copy something from off screen because I don't remember this syntax. So we can say name equals VM. I think that's all we need to do, actually. I think we just need to give it a binary target. And this should work. So what happens now if I say cargo run? Excellent. Failed to parse manifest. Can't find a binary at source/bin/vm or source/bin/vm/main. So let's make this file. Let's make a main function. Let's go. Oh, that's really annoying. I always forget that Vim doesn't like doing that. Cool. So we make a main function. Sleepy Mushroom says hello. Hello. Thank you very much for swinging by. I really appreciate it. How you going? How you going? You a Rust fan? You a Rust appreciator? Use crate. No, hold on. Use simple VM. VM. I think we just import it like this. Cool. And this should be something we can cargo not make, cargo run. Oh, sorry. It would be nice actually to probably re-export these if possible. And I think, hold on, I think I can do that, right? Because, what do I say? Do I go use crate VM? Do I do it like that? Is that gonna work? Yeah, no, hold on. But you go pub use, right? And then it works. Then everything's fine. Everything works. Our virtual machine needs to be mutable because, of course, like the whole point of a virtual machine is its state that changes over time as it runs instructions. Excellent. Expected result. Oh. Cool. Wait, hold on. What am I doing? I can actually just... Okay, so we have a virtual machine. It runs. It does literally nothing right now. All it does is print out the instruction that it reads from address 0. I, for some reason, quit Vim, apparently. I don't know when that happened. Let's add our git ignore. Let's add our cargo.toml. Let's add our source files. Let's just call the commit init for now. Okay, that's a good start. That's a really good start. I feel good about this. I feel good about this. This is the most significant Rust that I have ever written. It's taken us 40 minutes to get here. That's okay. That's okay. So where do we go from here? Well, let's add something very important. Hold. I should bring this up on stream. Hold on. Pop out chat. I'm sorry to call you out like this, but hold on, let me just... Oh, hold on. Let me swap to a better source so I don't give away that this is all just fake. Is that better? That's a weird angle of my face, but let's just like pull this together. That was like hold my bear. I love it. I love it. Thank you. I'm sorry to make fun of you. I don't know if English is your first language, but I don't know if that's an intentional typo even. I find that very amusing. Okay. So let's add something to our step. Our step, we need to increment the program counter, right? We need to increment our program counter. So we get our program counter, we get an instruction. At what point do we implement our program counter? Do we do that once the instruction's complete, or do we do it straight away? Well, we probably don't want to increment the program counter if we jump somewhere. Let's do it up front. Let's say self.registers equals PC plus 2, actually. We want to increment it by 2 because our PC, the address is the address of an individual byte, so we increment by 2 because they're 16-bit. Hold my bears when you redo this in Go. I've been writing Go professionally since halfway through 2022. I'm taking a bit of time off at the moment, and that's why I thought it would be good to learn Rust. But yeah, I'm a Go boy, and I really like it. I don't know if that's controversial for people, but I really like Go. Oops. Go's really nice. I think Go's good for writing like very enterprisey stuff with big teams because it's just hard to do things in weird ways. Okay. So we can see that as we're running our virtual machine, every step, our program counter is going to increment by 2, which is what you want. The program counter goes up. In theory, this means we read additional instructions, but for now, all our instructions are just 0. Okay, even better. Let's take this a step further. Let's actually add a thing, an instruction to our machine. And these are going to be our operations, and our first operation is just going to be not, and that's it. Frankity made a scraper which serves as an API for a mobile app. That's kind of cool. for fun and because he hates free anime sites with tons of ads. Incredible. Yeah, it's always cool when you can like take a bad website and just scrape the information out and make it better. I approve of this. Okay, so we have a 16-bit instruction. I guess we should decide what our instruction format's going to be, and let's just like jankily document this here. Instruction is, so it's going to be in, let's say, so this is an instruction. This is going to be our operator, and this is going to be kind of our arg to that operator. If this is, this arg will either be an 8-bit literal or 2 registers. Each register being 4 bits, because we only have 8 registers, that is more than enough to reference all of our registers. It's going to be a very simple instruction set. Extremely simple, okay? So, let's go let op equal leet. So our op is going to be the lower 8 bits, so that's just going to be instruction. Oops. Oh my gosh, my keyboard skills have really gotten bad. And then we just want to match op. If it's not, then... Oh wait, hold on. There's another thing I think we want here. Because we can't just match it. We got to like cast it into this somehow. How do I do this? Shit. I thought about this. I have done this before. When you define an enum in Rust, you can tell it that it actually represents the type that represents it underneath. So for example, if I made this I8, I could say that nop is -1, I think, or something like that. But this way, they're just going to be like, unsigned numbers, which is what I want. I'm just going to cheekily dash into my other screen. Actually, no, let's just do it on the screen. Screw it. It looks kind of weird with how I have my stream set up, but that's okay. That's okay. 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 But Go is a very productive language. Go is a very, very productive language. Cool. What are we looking up? Let's say Rust convert integer to enum. Can I do it? Try from, try into. Here we go, from primitive. Okay, this is what I want. This is what I want. Maybe without, I don't know if I want a dependency just for this though. This seems okay. Transmute. I'd rather not do something unsafe. Okay, let's just do this. Let's do this for now. X if X equals op. Actually, I don't think enums or types should have plurals in them. I think this is an op. It's not an ops. Like, the type is the set of all operators, but the actual thing, it's an operator. This is very picky and very, very finicky. Okay, so if it's a nop, then we just say nothing. We don't do anything. Add full through though. This is where shit gets spicy, because we're gonna say, well, hey, this is an error. And actually, this is gonna be what, this is gonna be the last thing we do. Our error is gonna say, oh no. Okay. Oh no. I guess this is a U16 now. Or maybe this should be a as U8. And again, I really hope that these casts are free, because it would kind of suck if they weren't. Could you do the casting at the top of the match? This is a good question. Could you do the casting at the top of the match block to avoid casting on each arm? This is complicated. Oh my gosh, can I please click on things without menus popping up? This is complicated, right? I don't think there is a safe way that I can cast op. So for example, right, I can't say as op, right? This doesn't work. Right, I can't do this. Because this only converts between primitives. So I'd need some kind of function to convert. The problem is, like, yeah, the thing I'm casting is not the operator, it's the actual enum member. So I could write a function that maps every integer into the enum. I don't know. I'm gonna basically have to have this kind of match statement anyway somewhere, so it may as well be here. Actually, maybe that's silly. Hold on, am I gonna need this somewhere else? I'm gonna need the inverse of it, right? I'm gonna need to go from a name of an operator. When I write an assembler, I'm gonna have to go from a name of an operator to a value, but that's not this. So myopic squirrel, I can't safely, like, I can do this. I can transmute it, but I would rather not do that because that's unsafe. I guess that's not the worst thing. I don't know. But the answer is actually yes. I could do this. I am choosing not to, even though it's much wordier. Cool. So when I run this, it does nothing, and that's what we expect. If I come into my virtual machine binary and I say write the value, write just some random value into address 0, address 0 being the operator of the first instruction we read, now it's going to crash. Now it's gonna, well, it's not gonna crash because we can't just arbitrarily write into a machine like that. I'm gonna be silly. This is very silly. And just make that public so that we can reach into it. And it fails now because it has no idea what this operator is. It's never seen this operator in its life. Let's change the type of this result to just be a string, so then we can say format I probably want to print it as hex. Then we do this. Excellent. So now we actually get a decent message. I'll write a better result type at some point, but for now, this is perfect. I'm going to take a quick breather to go to the bathroom, but when we come back, we're going to try and actually load a program into this that might do something a little bit more interesting. So back in a second. I've had a wave of inspiration while I've been in the bathroom, okay? And that is that, let's say we add another, operator. Let's say we have push, right? So, you know, the way I'm kind of thinking about things at the moment, we'd have push, we'd have pop, we'd have, let's say, add stack. Let's do this for now. Right? Push, pop, adds, nice and simple. So we can push numbers in, we can pop numbers off, we can add them together in a stack. We don't actually even need pop for this. Let's maybe also say store, right? Where we would oh no, actually no, let's keep it, let's call it pop. Let's call it pop, because pop will pop something. Let's call it pop reg. Pop something off the top of the stack into a register, okay? Now the problem is that these things are going to take extra information, and so the way we're thinking about it right now, we're just thinking about this part of the instruction. But what if we thought about it differently? What if we thought about it? What if we got rid of this? What if we said, well, push actually takes a U8, right? We can push a U8. Pop reg is actually going to take a register as an argument. We're going to pop something off the top of the stack into a register. Add stack doesn't take any arguments. It just operates on the stack. But let's say we have another add register. Well, this is going to take two registers and add the things in those registers together. So this is kind of interesting, right? This is a very different way of thinking about these instructions. But then we're going to need a function that says, for example, I don't know if these things still have integer indices. That is interesting to me. And I don't know what to call these. Are these like a Rust integer index of enum with data? With like getting the position of an index. This is exactly, yeah. For non-data. Derive partial ord. Or ord, right? Derive ord. Does that mean that... Does that mean I can do this? Okay. That sounds more like what I want. Maybe I can't do this. Maybe I need an additional mapping, right? Where... this is silly duplication, though. Right? Do I really need to do this? And then this is my repr U8. Is this what I have to do? This seems silly. This seems really silly. This seems so silly. If anyone has a better idea for this, please let me know. But so we'll have a function that goes something like this. Oops. Shit. I just destroyed my history, which is kind of silly. That's okay. We can write it again. Parse instruction. We're going to take an unsigned 16-bit number. We're going to return a result. Perfect. Okay. Now... X and so we can do this, right? And this is very wordy, but we can do this in one place. And it gives us a lot of structure. Because I guess when we write an assembler, we're more... Are we more interested in this or interested in this? Anyway. I think when we write our assembler, we're actually only going to care about this rather than the whole instruction. But when we're executing it, this is very useful. And this makes our life very easy because rather than having to decode all these bits here, we don't actually care about the format of the instruction when we're stepping through our code. This logic kind of lives up here. Does mem discriminant work for the thing I'm after? Oh, that sounds good. This sounds like exactly what I want. Returns the value. Ooh, discriminant t. If t is not an enum, discrimination may change if the enum definition changes. Ooh. Undivided to transmute from a discriminant into a primitive. Numeric validation as cast. If an enum has opted into having a primitive representation. Ooh, okay. You are spot on, Myopic Squirrel. Thank you so much. And it's possible to use pointers to read the memory location storing the discriminant. Ooh, so it's unsafe, but we can do it. Oh, this is exactly what I want. It's just ugly. Okay, I'm gonna do it. I'm gonna do it because this is just so much better. What's the usual like docstring deal with Rust? I don't know, so I'm just gonna do this. Okay, that's perfect. Thank you so much. That is such a lifesaver. And I'm actually just gonna call this op because it's a much nicer name. And we're gonna copy exactly this code. U8. Let's maybe say op value, maybe? Maybe? That's okay. And then we're just gonna copy and paste this. You've tainted my code with unsafe, but like, look at this. This is just so much easier. Okay, so if x equals, now we just say op nop, maybe op nop dot, wait, yeah? We just say this. Or maybe we even say pub fn equal. I guess we could also say this, x equals other dot value. And then we can say if op equal like this, maybe. Maybe? Is this worse? Is this uglier? I don't know. We have to type op twice. No. Okay, hold on. This is better. This is better. We don't want this dumb equal. Okay. Let's see if this works. So let's say op equals parse instruction. If it's an error, it's going to bubble up. Then we're going to match op. Not instruction. Let's say op nop. Okay. Otherwise, we have an unknown operator. And now we're actually going to get a name instead. What happens if I cargo run right now? Oh, hold on. I missed a very important check. If x equals the value this is now just op. We need to derive debug on this. Do I just keep adding things like this? Is this okay? Let's just get rid of this. I'm getting carried away. That's fine. Oh right, yeah, because I guess okay. Let's not get carried away. Let's not get carried away. Oh wait, hold on. Was all that was saying that I needed to do that? Am I making life really hard for myself? Forget it. Forget all these other things. I don't know what I'm doing. I'm just gonna focus on debug, okay? No, please. There we go. Okay. This needs a default case, which is just going to be an error saying unknown op. It's going to be an error with a format. Excellent. Excellent. Now we get the same error as before, which is good. Except now we can do more interesting things. So for example, if we have a push instruction, let's say, so we push, we want to get this arg from the bottom, which is going to be an 8-bit literal. Say x and FFOO. So we should be able to do this, right? Where we decode this arg from the instruction, and then we just have an instruction that has this there, right? Okay, now here's a problem. Method not found in... Oh. See, how are we meant to get this? So I guess this is like the ugly side of it, but we can just say 0. This probably churns a bunch more than it needs to. Shift right. Shift right by which would overflow. X is a U16. Oh, we've overloaded the word X. Hold on. Let's call this ins for instruction. There we go. Now we're back to the same error. Okay. But now we can say op push. And all we have to do, where before we would have had to do the decoding here, now our step function doesn't care about how these instructions are encoded. All we say is self memory. Maybe actually we need to get the stack pointer first. I wish there was a way to automatically convert these if the underlying representation was a U size, but anyway, I don't think we can do that. If anyone knows how to do that, that would be cool. We get the stack pointer, and maybe I should actually wrap this in a function or something, make it just a little nicer. We get the stack pointer. Now, when we push, we're gonna write a 16-bit value. No, we're going to write an 8-bit value because that's all we have. We're going to write at the stack pointer the value and get the result. Actually, no, we're going to do that because we're not going to increment the stack pointer if it fails because that's some kind of fault. We kind of like jump out here, and then we're going to say self registers we're going to increment it by 2. I think this makes sense. Because then, yeah, when you push, you write to the current thing the stack pointer points at, and then you increment it. When you pop, you come back 1 and then read what's there. Or come back 2, in fact. But yeah. So let's do this. Let's write pop while we're here, because we might as well. And what we say is... We have to read 2. We have to read 2 bytes at once. We're popping a 16-bit value into a 16-bit register. We're going to read at the stack pointer. Let's say if let sum v. So if we get a value out of memory here, then we say self.registers r as usize equals v. That's it, we just set the register. We should probably also make sure we're not just setting the stack pointer, but let's... Oh, actually, no, hold on. -2. Where do we de-increment this? If we successfully read it, then we de-increment it, I guess. Does that make sense? Is that okay? Is this? Yeah, I think so. Cool. Else. And this is just okay. This is also okay. Otherwise... Otherwise we have a memory fault, and we need to do something bad. So what happens if I cargo run this now? Oh, because this needs to be format, because we're actually using a format string. This write, if this fails, Okay. So what's happening? What's happening is we just want to differentiate between read faults and write faults. Eventually I'll use a structured error type for this. This needs to be a return because it's in the middle of a thing. I didn't mean to quit then, but that's okay. Okay, so we're back. We've got the same error. And that's good. We like this same error. So we've got this parse and run logic a little bit more down, which is great. Pop reg, register, add stack, add register. Let's implement these two just while we're here. And I like this. I like that we don't care about the encoding of the instruction when we're running the actual logic. Add stack. Now it occurs to me that we probably need a higher level pop. U16 string and push we need these higher level functions, otherwise we're gonna repeat ourselves an awful lot. So let's kind of just copy this code out. That's push. Oop. Extra level. Cool. And this is literally what we do. Self.push, just the value. Easy. Push is easy. Push is easy. Pop is a little bit more involved because of this register logic. That's not what we're actually going to do. This needs to come in. Oh. Extra layer there that I missed again. Okay, so get the stack pointer. If we read it correctly, in this case, we actually just send this out. Otherwise, there's a memory read fault. Now when we pop a register, we call self.pop. And then we say self.registers are as usize equals value. Excellent. That changes the semantics a little bit, but that's okay. That's okay. Beautiful, beautiful. That is so annoying. I don't know what key combination that is, but I keep doing something a little bit funny here. Self.registers are as usize equals value. Okay. When we add the stack together, we say let A equals self pop. Let B equals self pop, and then we say self.push A plus B. And we don't even, because push has the same return signature. Beautiful. I love it. And then, should I add register? Yeah. I should probably call this pop register as well. Just so that we're using full names for everything. It just feels better, right? We don't need to be brief here. All right. So this is going to be a similar thing, but let's say actually we can be quite brief. R1 as usize plus equals self.registers R2 as usize. Okay, and this is good as well because by the time we get to this point, we already know these are two valid registers. So there's actually nothing that can go wrong here, right? We've already done the bounds check. We're safe to just throw these in. Not 100% safe, you know, there are some cases where this could still blow up, but that, you know, is a problem up here. Ideally, by the time we get to here, we're just throwing it through. There's no failure condition. And the goal will be to keep these very, very brief, right? Because otherwise, if we just knew that this was an add register operator, we would have to pull out what the registers were. We're encoding this extra information in the actual like type, in the actual value. It's really cool. We know it's valid. If you haven't read the wonderful Alexis King blog post, Parse Don't Validate, highly, highly recommend it. Okay. So, we need to do a little bit more work though. So now down here, we definitely need to do more work. Let's, instead of copying this everywhere, because there are going to be lots. Actually, let's not do that yet. Let's just do things once first. X, if x equals op, pop. This is less clean than I hoped. This is less clean than I hoped, but that's okay. Pop register. So if it's a pop register instruction, then we're gonna say let reg equals. So what we're saying is, so 0, 0. So 0, 0, that's all these zeros. And then the first register will be this bit, right? These first 4 bits. So 0xF00. Still right shifted by 8. And then we're going to say OK, op. Oh no, hold on. Now we need to turn this number into a register. So let's say impl from there is actually a trait I can implement, a standard library one, but I don't remember what that is, and I'm running out of steam, so I'm going to keep this kind of simple for now, which is going to give us back a register. Now, this is where I can better use discriminant, right? Or just cast it to a, okay, I can just cast it. So, and so this, I have to do this silly cumbersome thing again, but it's easier here. A, B, C, M, S, P, P, C, V, P flags. C, M, S, P, B, P, P, C, B, P flags. And this needs to be an option, I guess. So all these need to get, okay. Let's write a macro to do this. And then I should be able to, nice. You can actually apply a macro to a range of lines in Rust, but I can never remember how to do that. So that's quite good. Then this is just none. So now, register from U8 op pop. Oh, that is op, not okay, okay. So if we get a register and it's a valid register, then yep, perfect. Otherwise, we have an error where we're going to say unknown op, unknown register. And we're going to do this in hex because it feels more natural. Okay. Does this run? No. You can convert a U8 into a U16. That sounds good. That sounds good. Oh no, hold on. This actually just needs to be a write to. I'm very silly. That is a useful error message. Wait, hold on. VMRS push. Oh, 109. It's when it gets called. I am widening, not narrowing. Cool. Function defined here. Expected U8 found a U16. Okay. Expected U8 and found a U16. That is not good. That is not good. We're just gonna dumb cast it down. I think that's okay. Unreachable pattern. Wow, okay, so this is good. We want to be exhaustive here. And actually, yeah, we want to get rid of this because we want to handle every single operation we define, especially if they're going to be this small. There's no reason not to. Wellington Carvalho says hello. Hello, welcome. Thank you for stopping by. I'm probably about to wrap up. I would love to run a simple program here, but we'll have to see. We'll have to see. So what can I do? Let's say add Well, actually, no, that should be enough. Okay, so this should be enough to do something kind of fun, as long as we can print a register out. I'm gonna make a function called getRegister. It's gonna take a register and it's gonna give us back a U16. And we're just gonna return self.registers R as usize. Perfect. Very, very simple. Very, very simple. Okay, so now when we come into our virtual machine binary, instead of doing that, so silly. So silly. Okay, so now we have a thing that does nothing, which is excellent. Once we're done stepping through a couple of instructions, let's print ln the value of the A register, which is going to be vm get register. And of course, this means that we need an OK at the end. Cool, so A is 0. Now let's write some code to put something else into the A register, okay? We're gonna do bits and bobs ourselves, and our program should look something like this. Let's say push 10, push 8, add stack, pop register A. Right, this is going to be our program. We're going to run 4 instructions, 1, 2, 3, 4, perfect. And now we just need to write it. So let's say vm memory write. So the lower 8 bits are going to be the op in this case. Let's make a split so that we can pull this up, because we need to see what these ops are. Okay, so push is going to be 1. And then we need the 8-bit value we're gonna, the argument to push, which should be 10. And we also actually need to tell it where to write this. So that we're gonna start, because our program counter starts at 0, eventually it will start at something that isn't 0, but for now, it will be like this. 2, we're gonna also have a push instruction. Oh my gosh, please. 3. And the value is going to be 8. Cool. So now we need an add stack instruction, which is going to be 0, 1, 2, 3. We don't need to write anything to address 5 because this doesn't take any arguments. So then 6, we want 0, 1, 2, a pop register instruction. And then the argument to that is going to be 0 because it's register A. Except it's only the first 4 bits of this 8-bit number, but that's okay. That's okay. So now if I run this, maybe we'll get something different. Unknown op 0x3. Excellent, excellent. Unknown op 0x3. 0. Did I not do add stack? I didn't do add stack. That's okay. That's okay. Okay. This is a little bit too hectic to read in this very wide format. Let's go add stack, which doesn't take any arguments. Let's get rid of the silly comma. And this should be a program that can run. And that works, kind of. So, I mean, interestingly, right, you would think that 10 plus 8 was 18. So what happens if I do 16? Am I going to get 14? 12. Okay, hold on. This is going to say 7, right? What the hell? It's deterministic. Okay, so it's reading the wrong value from somewhere. Clearly. 12. 12. What are you reading? Let's do a really dumb debug print line just for my sake. Oops. A, B, A plus B. 6 plus 6. Ah, so maybe we're not actually popping the stack properly. That might make sense because I think, yes, there we go. That makes sense. We're not actually changing the stack pointer because that happened after. Oh, perfect. Okay, now we can change the numbers. Let's go 18. As I intended. Let's get rid of this silly println line. Awesome. So we have a simple virtual machine and it's running actual code. And it's taken a long time to write all these little things because I don't know Rust. You know, if you do this in Python or something, you can hack this together so quickly. But this was a little virtual machine here in Rust. I'm going to flesh this out. I'm going to do a lot of stuff with this. Okay, this is just the beginning. If you think that if you think this is too janky, if there's a better way, please leave a comment and tell me because I would love to hear. If you think this is too janky and there's a better way, all this weird match stuff, please leave a comment and let me know because I would love to hear. This has been a journey. This has been the start of a journey. I actually was going to start this stream with a little template, you know, basically write this part ahead of time, but I thought let's just jump in, let's do, you know, kind of episode 0 and get the most basic thing running. My first priority next time is probably to start writing an assembler so that I don't have to poke individual bytes into memory by myself. That would be a nice quality of life improvement, right? Not having to be an assembler myself. Or at the very least, maybe writing a little Python program that takes a list of, you know, hex bytes and puts them into a binary file that we can load. You know, just not doing this, basically. So there's cool stuff we can do from here. But this has been fun. I hope people have enjoyed it. I hope people who are interested in Rust have found it interesting. I hope people who don't know much about Rust are intrigued to learn more. I'm definitely intrigued to learn more and see how far I can go with this. Thank you very much for tuning in. My name's Tom Marks, and I will hopefully catch you very, very soon because I hope to be doing a lot more streaming this year.